So, welcome to our land of remote learning. This is the way we've got to be for the next 3 weeks or so. Hopefully only 3 weeks, because really nothing at the end of the day can beat the face-to-face, the classroom situation. But anyway, this is where we are. This is what we've got to do for 3 weeks. So we're going to get straight into it. We're going to go into acids and bases. Now, acids and bases will lead us into what we call volumetric analysis. That's why I'm hoping we're going to be back at the end of this chapter, because volumetric analysis is how we put this thing to work in terms of using specialized equipment like burettes and pipettes and volumetric flasks and conical flasks, etc., etc. And we bring back the mole into the whole idea of liquids. So I'm going to get straight into acids and bases, and I know straight away that when I mention the word acids and bases to you, you've got certain words in your head. Okay, now the first thing I want to draw your attention to is the symbol that we see up there in the top left hand corner. Those symbols, by the way, the triangles are gone. You might just want to do a quick Google search and see that the new symbols are actually diamond shaped, okay, like that. Now they have exactly the same thing, the hand and the bench and the caustic warning, but they're just orange this time. Okay, so just check that and make sure you understand that the old triangles are gone and it's now an orange, kind of a diamond shape on its side that they use in order to show the same symbol. But that symbol simply means caustic. Okay, it burns through materials, it burns through flesh, and it burns through other materials. So when we're using acids and bases, obviously we've got to be careful with skin, we've got to be careful with clothing, but most importantly we've got to be careful with eyes, because if an acid gets into your eye, it'll burn it. Okay, and unfortunately, as to date, there is no cure for blindness. So we've got to be very, very careful when we're dealing with acids, that we keep them well away from our faces. Goggles on all the time, screens on even. I think we might bring back the old visors when we're dealing with acids and bases, just to make sure that our faces are protected and so on. Anyway, that's what that symbol means, okay? But just think to yourself, when you hear the word acid, what do you think? What words come to mind? What descriptives would you use in order to link the English language with the word acid? Okay, and I'm sure for some of you, the very first thing you'll think of is dangerous, but that's not always the case. Acids can be dangerous, absolutely, but acids can also be very harmless. In fact, acids are responsible for the flavouring in food. Acids are responsible for, I suppose, the production of certain substances. Acids are also highly corrosive and highly dangerous, but it depends on where the acid is placed on a certain scale we'll talk about later on. But obviously, if you were to ask a little child what's an acid, the first thing to tell you is it's dangerous, and nearly all of them would understand it burns. Okay, so therefore we talk about being dangerous, we talk about burns, we also talk about dissolving. Now, if you take a look at the benches in my science lab, you'll notice that there are brown circles on the tables, which are not heat burns but chemical burns, where drops of sulfuric acid have actually hit the table. Okay, they do actually wear away the table very, very quickly. Nitric acid will be even stronger again, so we've got to be careful with them. So they do dissolve. But the one thing that very few of you would mention back to me is that, oh, an acid is any substance that has a pH of less than 7 on the pH scale. Okay, this one here. And if you remember what the pH scale is, the pH scale is nothing more than a scale that allows us to calculate the strength of an acid or a base. Okay, now slap bang in the middle of the pH scale is the figure 7, and 7 as a pH is the one that we always refer to, because 7 is the neutral pH. All right, then you've got two sides, 7 up to 14 and 7 down to 0. Now, one thing I do want to say is this: the pH scale doesn't begin at 0 and doesn't stop at 14. It goes below 0 and it goes above 14. The only reason why we focus on 0 to 14 is because that's where 99% of the world's acids lie. Okay, but there are acids that lie below 0 in the pH, and there are acids that go above 14. Very few, non-consequential to us. We don't use them, we don't talk about them, not in the course. So we're going to stick with the part, I suppose, the section of the pH scale that runs from 0 to 14. So 7 is slap bang in the middle. Anything below that is acidic in nature. Okay, that's one thing you've got to remember. Also, when we talked about an acid in junior cert, you had a definition. An acid was any substance, if you can remember, that had a sour taste. So if you think of a lemon, for example, or you think of a lime, or you think of anything that's sour, yeah, especially these, what are these little jelly sweets you buy with all that horrible kind of a soury sugar on the outside? like jelly worms or sour soothers or things like that, those crystals are citric acid. And the citric acid, when it hits your tongue, dissolves, and therefore the acidity of that particular citric acid then is felt by the tongue. That's sour taste. All right. So one of the quickest things we can do to test an acid is to see if it has a sour taste. However, you ain't going to do that to sulfuric acid. You're not going to do that to hydrochloric acid. You're not going to do it to nitric acid. So there has to be a safer way. And I'll talk about that in a moment. All right. But basically, a sour taste is one of the ways we know. For example, sour milk. What happened? Sour milk has a build-up of what's called lactic acid. And lactic acid is built up by the action of bacteria in the milk that simply drop the pH below 7. And once the milk's pH starts to drop, the milk begins to curdle. And then you get clots in the milk, which is actually cheese, by the way. But at the end of the day, people don't like that floating around in their tea. So the milk goes sour, sour taste, out it goes. Okay, so just keep that in mind. Acids are substances that have a pH of less than 7. Yes, they're dangerous. Why? Because they're caustic. It's another word. They burn. Caustic, dissolve and burn can be both considered as being caustic. And they have a sour taste. And you can watch that video down there below yourselves when you get these slides sent to you. What about bases, on the other hand? I'm always surprised that when we're in class and I ask people about what's a base, none of them can tell me. Everybody knows what an acid. Oh, an acid is dangerous. An acid burns. An acid has a sour taste. And then I talk about a base, and nobody seems to know what a base is. Okay, and I'll give you a hint. Look down at the bottom right of this particular slide. Look down here. Soap. It cleans. Okay. Usually anything that cleans has a pH of above 7. Now, if acids have a pH below 7, well then bases will have a pH above 7. Okay, and 7 itself is kept for the neutral substances. Again, notice the same symbol up here, the same caustic symbol, not the triangle but the diamond nowadays. It burns, it dissolves. You've got to be extremely careful. The same safety procedures with bases as we use with acids, all right? But there's one extra thing about a base that distinguishes a base from an acid, and that is that when you get a base on your fingers, it has a soapy feel, okay? It actually feels like liquid soap. And the reason for that, which you will be asked in the questions later on, is because the base is able to turn the fat into soap. There is an experiment we'll do in 6th year called base hydrolysis. And what it does basically is it just takes the lipid that's on the surface of your skin and it turns it into soap. So when you feel that soapy feel of a base, you know the base is doing the job it has to do to turn the lipids into that soap, and underwater then it feels extremely soapy. One interesting thing about acids and bases is this. If you spill an acid and a base in your hands, you can't wash it off. You can dilute it, and dilute it hugely. So if you do get a spill of acid or base in your hands, you go to the tap immediately and you simply use copious amounts of water on your skin, run it well, wash it well, and keep it under the water for quite a while to dilute the acid and base down so that it doesn't do any damage on the surface of your hands. So, can you remember how we described a base? A pH of greater than 7, it's corrosive, it dissolves, kind of similar to an acid as well, except for the fact that the pH values are up the other end, all right? But we also say that bases have a soapy feel because bases react with lipids to turn the lipids into soap. So bases turn lipids, which are fats by the way, into soap. That's why bases, when they get onto your hands, produce a soapy feel. Lipids, by the way, are fats and oils. In case you're wondering, I think you may have done that in your junior cert. If not, those doing home ec will know exactly what a lipid is. A lipid is a group term for fats and oils. None of these descriptions actually reveal what an acid or a base is. So when we talk about acids and bases from junior cert knowledge, we're describing it. Oh, it has a pH of less than 7, it's an acid. Oh, it has a sour taste, it's an acid. Oh, it has a soapy feel, it's a base. Oh, it has a pH of greater than 7, it's a base. But what we don't actually know yet, coming from junior cert, is what an acid is. How do I describe all that group of substances that have a pH of less than 7? Why do they have a pH of less than 7? What's the reason why the pH drops below 7 and then gives these things an acidic nature? Well, in order to answer that question, we look at, first of all, litmus paper. Now, if you remember in junior cert, if I put out 3 beakers and one had a colourless liquid, and 2 had a colourless liquid, and 3 had a colourless liquid. But if I was to tell you that one of those three is an acid and one of those three is a base. Probably at that stage, if I asked you to figure out which is which, you're not going to put your finger and taste it. No. You're not going to smell it. No. We don't touch, taste, smell, drink, nothing in the lab. There must be another way for me to be able to figure out which one is an acid, which one is a base, and which one is neutral. The key thing we used back in junior cert was litmus paper. We had two types of litmus paper. We had red and we had blue. Okay. The red litmus paper remains red in an acid. The blue litmus paper remains blue in a base. Or to put it another way, the blue litmus paper turns red in an acid and the red litmus paper turns blue in a base. Okay. Now here's the problem. If I take red litmus paper, and I've got three beakers, don't forget, three colourless liquids. Okay, one is an acid, one is a base, one is neutral. If I take up the red litmus paper and put it into the first beaker and it stays red, is that guaranteed to be an acid? Think. Is that guaranteed to be an acid? Could it be anything else? Which other substance there doesn't have any effect on litmus paper? Obviously the neutral one. So by using one piece of litmus paper, we're not going to be too sure as to whether it's the acid or the neutral one. So what we should normally do is this. Into the three beakers, you put a small piece of red and a small piece of blue. And in the beaker where both litmus papers turn blue, that's guaranteed to be the base. In the beaker where both litmus papers turn red, that's guaranteed to be the acid. And in the beaker where the red and blue stay red and blue, well, that's guaranteed to be the neutral substance. So it's not enough for us just to use one strip in a solution. We must use the two and see what effect the liquid has on both of these pieces of litmus paper. And as I said to you already, the red one is the sign of an acid. The blue one is a sign of a base. And if there's no change in either, it's a sign of being neutral. But again, the litmus paper is revealing that the acid and base are doing something to the chemical in that paper to turn it that colour. But we're still left with the question, what is an acid, what is a base? So let's just, before we move on, summarise what we already know. Acids have a pH of less than 7, they have a sour taste, they're corrosive, and they turn litmus paper red. That was the definition you had in your junior cert. And likewise, bases are completely the opposite. pH of greater than 7, soapy feel, corrosive as well, but they turn litmus paper blue. And there was one other piece of paper that we could have used, which I'll mention here, but I'll talk about later on, which was called universal indicator. Now, universal indicator revealed the strength of the acid or the base. Here, down at this red, strong. Up here, neutral. And up here, that's a strong acid, by the way. Down here, strong bases. So we're moving from neutral to strong acids this way, and from neutral to strong bases this way. So what we normally do with universal litmus paper is we throw a piece into a solution, let it change whatever colour it goes to, and then match the colour of the paper off this little chart that's on the front of the cabinet, not front of the container, and then match off the pH. Okay, so that's a universal litmus paper. I will talk more about it, but litmus paper does not reveal the strength. Litmus paper just reveals whether it's an acid or a base. The universal indicator, what will that do? The universal indicator will tell us the strength of the acid and the base in terms of a value which we call the pH. Okay, so who was the first person to put forward an idea as to what acids are? The guy is called Arrhenius, all right? And Arrhenius, having studied all the acids that were available to him at the time, discovered one particular important quality about acids. And what he discovered was that acids always broke up when you put them into solution. So as soon as you poured an acid into solution, it broke up. The molecule that was in the original acid broke up. And one part of that particular dissociation, you'll see the word there, dissociate means to break up, was always a H+. Okay, so what Arrhenius said was, if I take a substance and put a substance into water, and if it breaks up to give me H+ ions like that, then that particular substance is an acid. Now, something important there. He proposed that acids were substances that dissociated in water. So what he's basically saying is that if an acid is going to be acidic, it has to be an acid in water first. So if you take hydrochloric acid in its concentrated form that is not in water, it won't show acidic properties. It must be placed into water, so that it breaks up and releases copious amounts of H+. And if it does that, it is then known as being an acid. Okay, so keep that word in mind also, dissociate. So the definition of the Arrhenius acid is as follows. An acid is any substance which in water dissociates, use the proper word, dissociates to give H+ ions. Got it? Arrhenius, again, an acid is any substance that dissociates in water to produce H+ ions. Okay, and then of course there's the obvious question. Well, if an acid produces H+ ions, and I now know that when you put it into water it breaks up and gives H+, what does a base do? And again the same thing. Arrhenius developed a definition for what a base was, and he simply discovered that if you placed a base into water, a dissociation also took place. So the base broke down, okay? But when it broke down, it continuously released what we call OH- ions, like that. So bases in water produce OH, acids in water produce H+, meaning that it must be the H+ and the OH that are causing the litmus paper to turn red or blue, or the universal indicator to have a particular colour. Okay, so just link those two together in your head for the moment. We'll come back to it again later on. But that's what the definitions you've got to remember. So Arrhenius was the first person to put forward a theory for what is an acid. And here's what he said. An acid is any substance that dissociates in water to produce H+ ions. He also said about a base is any substance that dissociates in water to produce OH- ions. So they were the very first two definitions that were given in terms of an acid and a base. Now, go back again to what we said already about acids and bases. Acids, sour taste. Bases, soapy feel. Soapy feel means that bases are extremely good cleansers. And one of the most widespread used base is toothpaste. So you're putting in something with a pH of greater than 7 you're cleaning your teeth, because the bacteria on the surface of your teeth are producing acid. And as they produce acid, the pH of your mouth drops. And unfortunately, low pHs damage the enamel of your teeth. So you wash your teeth with toothpaste in order to bring the pH back up to safe levels to protect your enamel. Just a little bit of chemistry in an everyday washing of teeth. So what is dissociation, as I said already? Dissociation is breaking up. Okay, that's exactly what it is. So when I take, for example, HCl, and I put HCl into water, it will break up into H+ and OH-. Okay, when I take HNO3, which is nitric acid, put it into water, it will break up into H+ and NO3-, and so on and so forth. And the key thing to remember is hydrogen chloride produces H+ when it goes into water. HNO3 produces H+ when it goes into water. So therefore, under the Arrhenius definition, both of those substances are acids. Okay. Acids that dissociate to produce one H+ are what we call monobasic or monoprotic. Now I'm going to use the word monobasic because that's the one that's used in the exams. So for example, as I told you already, HCl, HNO3. But there are other acids like H2SO4 and H3PO4. Okay, now what happens here? When that goes into water, it breaks up into two H+ and SO4 2-, sulfate radical. I hope you remember your radicals, they're extremely important. This one, when it goes into water, breaks up into three H+ and PO4 3-. But again, the H2SO4 produces H+, the H3PO4 produces H+. Both of them produce H+, which means that both are acids. But this one, per molecule of H2SO4, produces twice the amount of H+. And this one here, for every molecule of H3PO4 that breaks up, it produces 3 H+. So now we're beginning to see that not only are acids substances that dissociate in water to produce H+, different acids produce different amounts of H+. And now we might have a little bit of a clue as to why one acid is considered to be strong and another acid is considered to be weak. Maybe it has to do with the quantity of H+ that it can push out in water. And again, as I said, we'll explore that later. What about the H2SO4 or the H2CO3? In this case, that molecule produces two hydrogens, H pluses. And this molecule also produces two H pluses, which means that they are dibasic. Okay, HCl produces one, HNO3 produces one, monobasic. H2SO4 produces two, H2CO3 produces two, dibasic. And finally, H3PO4 molecule produces 3H plus, which we call tribasic. Now, the words monobasic, dibasic and tribasic simply refer to the number of replaceable hydrogens in an acid. So HCl, 1H, monobasic. H2SO4, 2H pluses, dibasic. H3PO4, 3H pluses, tribasic. So the name mono, di and tri is simply linked to the number of replaceable hydrogens that are present in that acid. And acids, by the way, always begin their molecular formula with the replaceable H's. Okay. So as I said to you already, let's consider H2SO4 and H3PO4. Now, H2SO4 and H3PO4. The first to be recognized here is that H2SO4 has two hydrogens. H3PO4 has three hydrogens. And if we were to ask you a question, which one of these two molecules gives more hydrogen? Your answer would be obviously H3PO4. Let's just take a look at our molecules. So there's H2SO4 and there's the two replaceable hydrogens. Here, there's the three replaceable hydrogens. Okay, so we would be under the impression that because H3PO4 has three hydrogens per molecule and H2SO4 only has two hydrogens per molecule, that maybe H3PO4 produces more hydrogen per molecule or more bang for the buck than H2SO4 does. Here's the unusual thing. H2SO4 is found in carboxylic acid. H3PO4 is found in your can of Coca-Cola or Fanta or Smithix, I was going to say, could do with a beer. No, not Smithix, of course. Sprite. Sprite or 7-Up or one of these things. Huh? H2SO4 is found in car batteries, will strip your skin in seconds. H3PO4 is in the can of fizzy. Why? Well, obviously, if H3PO4 is edible and H2SO4 is to be kept away and be treated with extreme caution, then in practice, H3PO4 is weaker than H2SO4. And what's the reason for that? It must be more than just the number of hydrogens per molecule. And that's what we're going to look at here. Why is H2SO4 so much stronger than H3PO4? And the reason is, as I'm going to show you here. Let's take HCl. Now, let's take 400 molecules of HCl. Every molecule of HCl has one hydrogen. But here's the key thing. When you put all 400 of these molecules into water, all of them dissociate. They all break up. So therefore, 400 molecules of HCl will give 400 H pluses, which is very, very strong. Okay, let's move on to H2SO4. H2SO4 has two hydrogens per molecule. Now, if I put 400 molecules into water, all of them dissociate, which means that the 400 molecules will produce 800 H pluses, which is extremely strong. But finally, if I take 400 molecules of H3PO4, only 1 in every 100 will actually break down. Okay, so that's extremely alarming. Only 1 in every 100 will break down, meaning that out of 400, only 3 of them will actually break up. So H3PO4 contains 3 hydrogens, but out of the 400, only 1 in every 100 will dissociate, meaning only 3 molecules will break down. 4 molecules will break down. And 4 molecules will give their 3 hydrogens, giving you 12 H pluses, which is very, very weak when compared to the other 2. All right, so let's go through that again. Hydrogen chloride, every HCl produces 1 H, but they all break down. So therefore 400 HCls will give 400 H pluses. H2SO4, 2 H's per molecule, all 400 dissociate, 400 times 2, 800, extremely strong. And lastly, H3PO4 has 3 H's, but only 1 in every 100 will actually break down. The rest all stay together. All right, and because only 1 in every 100 dissociate, that means only 4 molecules will break down, meaning 4 molecules will give you their 3 hydrogens, which only produces 12 H pluses, meaning it is extremely weak when compared to hydrochloric acid and sulfuric acid. Hence the reason why we can drink phosphoric acid, but we cannot drink hydrochloric acid or sulfuric acid. I hope that maths makes sense to you. If not, you know where I am. Send me an email and I can go through it with you again. So, what's dissociation? Dissociation is breaking up. So if you want to break up with your boyfriend or girlfriend, tell them you're going to dissociate. Simple as that. They won't know what you're talking about. It's much easier. You don't have to do it by phone, then you can just say, I'm dissociating, end of story, gone. Won't have a clue, it's hit them. So that's what dissociation means, breaking up, okay? The power of an acid depends on its power to produce H+. Now that's extremely important. So go back over what we said already. An acid produces H+. Okay, Arrhenius said an acid is any substance when you pour it into water gives you H+. But then we begin to realize that some acids like lemon juice and phosphoric acid are edible. Citric acid, edible. Other acids like nitric acid and sulfuric acid are extremely caustic and have to be kept away and treated with extreme care. Why is it that some acids are strong and some acids are weak? Here's the answer. It's got to do with how much H+ they push out when you put them into water. If they push out a lot of H+, they're strong. If they push out a little bit of H+, they're weak. Okay, so when we talk about strong and weak, we're talking about the ability of an acid to do something, the ability of an acid to act as an acid. And if you've got tons of H+, by God, that acid will work very, very well and be very, very strong. Strong acids, therefore, dissociate well. That's extremely important. They dissociate well and they produce many H+ ions in water. Whereas the Purell weak ones, on the other hand, weak, they dissociate badly. That means that they don't break up. You put them into water, they stay together. Maybe 1 in every 100 might break apart, but most of them simply stay together as that molecule and don't give you many H+. And because of the fact that we've got few H+, the acid ain't going to do what it's able to do. Here, when we get a lot of H+, we get a lot of acidic activity. So few H+, little acidic activity, call it weak. Many H+, gives a lot of acidic activity, which we call strong. Okay, so when we talk about producing H+, what do we mean? Now I need you to think about this. I want you to look at this slide carefully. Hydrogen is obviously the most basic element on the periodic table. Periodic table, yeah? Hydrogen, number 1, up here somewhere. There it is, up there. It has 1 electron and 1 proton, as shown in that diagram. Now, notice the plus. See that plus there? Can you remember what that means? H+ means that this poor hydrogen has actually lost its electron. Watch what happens. And because it's lost its electron, the only thing that's left is a bare proton. Meaning that what was H has become H+. Now here's the problem. A bare proton simply cannot exist on its own. If we go back and take a look at what it was beforehand, there it is there. It has the electron and the proton interact with each other quite well, and that's fine. But as soon as a hydrogen atom loses its electron like that, it becomes a H+ ion. And the H+ ion is better known as a bare proton. And as I say on this slide here, bare protons cannot exist on their own. So what do? How does it exist? Okay, now you've got to remember that acids act acidically when you put them into water. Now there's the hint. So if you put an acid into water and it breaks up into H+ and OH minus, right? Or sorry, H+. I'm thinking of the water molecule here. Sorry, take that back. When you put acid into water and it breaks up into H+, it gives you your H+. The H+ is a bare proton. What does the bare proton do? The bare proton wants to piggyback on something. It needs to join to something. What did you just put the acid into? Water. What does the bare proton do? It attaches itself like this to a water molecule. See that? So there's your H2O there's your water molecule, and there's your piggybacking H+, which means that you now have 1, 2, 3 hydrogens. See the name down there? H3 and an O. But notice that it has a plus. So what happens basically is that the H+ that's produced by the acid can't exist on its own because it's a proton. So it attaches itself to the nearest water molecule, which is neutral. And the water molecule, like this diagram here, carries the H+ as a H+ almost on its piggyback. All right. The water remains neutral. It's carrying a H+, it's carrying a proton. So therefore, the proton is able still to act as an individual proton, albeit combined with a water molecule. So if you have a H+ and you add it to a water molecule, what happens? You're going to get H3O and a plus. Okay. Now, because H2O is neutral, really what that means, and what scientists say is, look, you can forget about mentioning the H2O. Let's just call it H+. So as far as we're concerned, H+ does not exist on its own. Okay. We know that it piggybacks on a water molecule to give H3O+. That's correct. But science dictates that we can take a shortcut. And when we're using the symbol of H+, we are under the impression that it's not H+ as a bare proton, but the bare proton being carried by a neutral water molecule. All right, so keep that in your heads. So this is known as the hydronium ion. So H3O+, apologies, H3O+ is the hydronium ion. What is it? It's a proton being carried on the back of a water molecule. And it only happens as soon as you add in the acid to the water. The acid produces H+, the H+ sticks on the back of a water molecule, floats around the stuff as H3O+, but in essence is acting as if it was a single bare proton, which we call H+. Okay, so there's a picture of what happens. There's your HCl, your strong acid. Strong meaning that it will produce a lot of H+. Okay. When this H+ is released, what does it do? The H+, when it's released, simply finds a water molecule and piggybacks on it. And you'll notice now that the H2O is still there. There's the H+ piggybacking on the water molecule, giving you what's called the H3O+ hydronium ion. And that's extremely important. Okay, so it dissociates, breaks down here. That's dissociation, break up. The H+ will then move on to the piggyback of a water molecule. The water molecule here carries the H+ as a hydronium ion. And then what about the Cl-? It minds its own business, just floats around the place. The Cl+ is not our interest. Cl- should say is not our interest. Our interest is what happens to the H+ on the back of a water molecule. So if we want to take this a step further and give it a proper name, okay, go back to what the hydrogen atom is. The hydrogen atom is an atom that has one proton and one electron. When it loses the electron, it becomes just a bare proton. Now here's my question. How could that bare proton now act like the nearest noble gas, which is helium? Wouldn't it have to gain 2 electrons? Look, so you've got your H+ and your H2O giving you H3O+. Look at this. So you've got your hydrogen, there's your nucleus, there's your proton, and there's your electron. Okay. Now, it loses its electron and it becomes a single proton. That single proton wants to have the same number of electrons as helium. So what does it have to do? It would have to find 2 electrons from somewhere in order to fill out the first energy level to become like helium. That means that the bare proton needs 2 electrons. Okay, the hydrogen atom only needs 1 electron to become like helium, but the bare proton here needs 2 electrons to become like helium, which means that hydrogen ion, the H+, has nothing to offer any atom that is willing to give it 2 electrons. So if the bare proton is going to form a bond with another atom and try and get the same electronic configuration as helium, then the bare proton has to take 2 electrons from the combining atom and give nothing into the bargain. Okay, and that's why we call it a dative covalent bond. So there's your water molecule. Now, Think of the H plus out here. H plus wants to be like helium. In other words, it needs 2 electrons. Take a look at the water molecule. Look at these 2 electrons here. That H plus will attack this water molecule. It'll pull both of those electrons to itself, taking both electrons from the water molecule and giving nothing back to the water molecule in return. That's what a dative covalent bond is. It's a covalent bond that is formed when one atom donates both electrons into the covalent bond to hold it together, and the other atom that comes forward gives nothing into the bargain. All right. Okay, so let's take a look. H plus comes in. Notice H plus is a bare proton, needs 2 electrons to be like helium, sees the 2 electrons down there on the water molecule, comes in, takes them, joins to them, but gives nothing into the process. So now we've got a situation where hydrogen has the 2 electrons, now it's stable like helium, and the water molecule becomes what? H3O with the plus that's already there as well. It's H plus, H3O plus. So that's your hydronium ion. Okay, so this new bond is called dative. Now please remember that, that's a key word, and it has been asked umpteen times before. What's a dative covalent bond? A dative covalent bond is when a covalent bond is formed by one atom giving both electrons into the bond, and the other atom produces or gives nothing. All right, so the H plus has no electrons to give, it's a bare proton, comes in and takes both, settles down and stabilizes like helium, and poor water molecule has to give 2 electrons in order to keep that bond together. So this new bond is called a dative covalent bond. Since both electrons in the bond between the H plus ion and the H2O are from the oxygen atom. So please keep that in mind. There's the dative covalent bond. Both electrons given to this to make it stable like helium, nothing given back from the H plus. So a dative covalent bond is formed in that way. Okay, so the above examples show the essential role water plays in dissociation. Acids will only show acidic properties when placed in water, and likewise bases will only show basic properties when placed in water. So it's extremely important that we make solutions of these acids. Okay, now that brings in 2 more words. That brings in words dilute and concentrated. So now you've already got weak and strong. Weak is an acid that produces very little H plus. Okay, strong is an acid that produces a lot of H plus. But the words weak and the words diluted and concentrated only refer to the amount of water that you add in. So if you add in a tiny amount of water, then you're going to have a very concentrated acid. If you add in a lot of water, you're going to be using dilute acid. So go back to your Ribena, or go back to your concentrated orange that you used to have when you were kids. Sometimes you'd come in and you'd take up the concentrate, you'd pour it into a glass, and then you'd fill it up with water and you would taste it. And you could hardly taste the Ribena, or you could hardly taste the orange because you made it too dilute. Now, was that the orange's fault? No, that was the water's fault. Too much water. So too much water means dilute. Little water means concentrated. Strong means plenty of H plus produced. And weak means little H plus produced. And please don't mix up the terms. So it is possible to have a dilute weak acid, a dilute strong acid, a concentrated weak acid, and a concentrated strong acid. Okay, concentrated and dilute refers to the amount of water being used. Weak and strong simply refers to how much H plus the acid produces when it gets into water. And it's important not to mix those 4 terms up. So go back to poor Arrhenius. Was he correct? Well, he was for a number of years, until people began to realize we've got problems with this thing. All right, and first of all, the first problem we have with Arrhenius is that they don't produce H plus ions. Think about it. He said an acid is any substance put into water produces H plus ions. But now we know that H plus ion doesn't exist. It's a bare proton. So they don't produce H plus ions because they produce bare protons. So it's probably more realistic to talk about an acid being something that actually produces protons rather than H plus ions. Okay. Secondly, protons can't exist on their own. So therefore, where do they go? All right. We already know if you put them into water, they piggyback on a water molecule. But if you put them in with something else, will they also piggyback on that other substance? The answer is yes, because they can't exist on their own. Another problem of Arrhenius is this. Arrhenius said in order to be an acid, the acid had to be in water. In order to be a base, the base had to be in water. So as far as he was concerned, acids and bases were confined to being in the aqueous mode. Okay, but that tells us then that you might be able to have acid-base reactions in the air or in gases, and we know that. All right, but it also tells us that other solvents are excluded. So is it only an acid when you put it into water, or could it be an acid when you put it into some other liquid? Of course it could be. All right. And lastly then, as I said to you already, some acid-base reactions happen in the gaseous phase. So it's possible for me to release a vapor of one substance, release a vapor of the other substance, and when they meet together, it is possible for them to act acidically and basically. All right, so keep that in mind. And again, there's a video down here that you can watch in your own time, which will bring you through some of those examples of where Arrhenius was wrong. So 3 problems with Arrhenius' theory. Bare H+ ions do not exist. Secondly, it doesn't only have to be water. There are other liquids out there inside which substances can act as an acid and a base. And finally, substances can act acidically and basically outside the medium of water in the gaseous phase. So poor Arrhenius, what did he say? An acid is any substance that produces H+ ions in solution. A base is any substance that produces OH- ions in solution. Problem. Number 1, H+ ions don't exist, bare protons. Number 2, it's not just water, it can happen in other liquids. And number 3, sometimes you don't even need water, it can happen in the air, it can happen in the gaseous phase. So these 2 lads, Bronsted and Lowry, one which is Swedish, the other which is English, and if you take a look at the name you'll know who's who. Bronsted, obviously the Swedish guy, Lowry, the English guy. Surprisingly, both worked on the same theory at the same time and got the same results, and neither of the other knew that the work was being done by the second person. Okay, so when their findings were released in around the same time, this whole theory was named after both of them because their results were exactly the same. But Bronsted and Lowry wanted to modify Arrhenius' theory. And basically what they said was, okay, the problem with Arrhenius is we don't produce H+, we've got bare protons. That bare proton then piggybacks on something else. So in essence, what's happening is the acid is throwing out a proton for something else to catch or something else to carry. All right. So therefore, the acid will produce a proton and it will give the proton to something that's willing to carry it. Now that's the model that Bronsted-Lowry said was important for acids and bases. So what they discovered was that a Bronsted-Lowry acid is any substance that simply is able to give protons to another substance. Now reverse that. If the acid is giving the proton, then the other substance has to be ready to take it. And the other substance that takes the proton is the base. So Bronsted-Lowry theory had 2 new definitions for an acid and a base. Number 1, an acid is any substance that donates protons. Number 2, a base is any substance that accepts the proton. All right. So an acid is a proton donor and a base is a proton acceptor. Other substances now, under this definition, become acids and bases because H+ was too restrictive. Okay, the bare proton opens up the field and brings in far more substances that can act acidically and basically without the presence of H+ or OH-. So Bronsted-Lowry were responsible for taking the narrow Arrhenius definition of an acid being any substance that in solution produces H+ ions and a base being any substance in solution that produces an OH- ion into the very wide but short definition of, hold on, an acid is any substance that donates a proton, a base is any substance that accepts that proton. Simple as that. Now, have a look at the following. HCl plus H2O gives H3O and Cl-. In that reaction, we can see the transfer of the H+, because the HCl breaks, produces the H+, which is immediately donated to the H2O. Now, the H2O will only carry the H+ if it accepts it. So therefore, this is the donor and this is the acceptor. Meaning what? This one here is the Bronsted-Lowry acid and this one here is the Bronsted-Lowry base. Okay? So the HCl donates a H+, Bronsted-Lowry acid. The H2O accepts the H+, Bronsted-Lowry base. Okay, but look at this one. The donation and acceptance of the proton happens simultaneously. Now, look, if you wanted to give a sweet to your friend, okay? And you really want to give one of these lovely, let's think of what do I like, oh, juicy fruit pastilles, okay? So you've got this beautiful blackcurrant, juicy fruit pastille that you want to give to your friend. Do you just drop it on the floor and hope that the fruit pastille is going to crawl up their leg and into their hand and then into their mouth? Or do you actually have to put it into their hand? Think of the transfer of a sweet. I don't even have one here to show you. But if you transfer something, the transfer only takes place when one person donates and the other person receives. It's a simultaneous process. You don't throw the H+, you don't throw the sweet, you don't throw it on the floor and hope that it crawls over and finds its way into your friend's mouth. No. You've got to donate and accept at the same time. Very simple. Donate and accept. It's a simultaneous process. It's not donate and then half an hour later with this thing hanging in the air you accept it. No, simultaneous process. So Bronsted-Lowry acids and bases act in pairs. So if something comes along and donates a proton and the other one takes it, the donor is the acid, the acceptor is the base. Alphabetical order, A, B. The acid donates to the base. A, B, acid to base. So there we have a quick picture there. Here, have a proton. Now I always think that proton's been a nice, juicy, blackcurrant fruit pastille. Okay, here, have a sweet. Oh gee, thanks, and you take it. That's the simultaneous process of donation. If it happens for us, it happens for acids and bases as well. Now, consider the following reaction. Let's take a look at this one. NH3 and H2O give NH4 plus and OH minus. I want you to think for a couple of seconds. Who has donated the H plus and who has accepted the H plus? In this case, one of the H pluses comes from the water molecule and it's donated over to the NH3, which turns it into NH4. Meaning, and then obviously the water then is reduced down to OH minus, meaning that the H2O is donating the proton to the NH3. So that's the Bronsted-Lowry acid and that's the Bronsted-Lowry base. Watch. H2O is now an acid. Under Arrhenius' theory, water would never have been considered an acid. Under Bronsted-Lowry theory, because water can donate a proton to the ammonia molecule, water, under Bronsted-Lowry theory, becomes an acid. And ammonia becomes a base. So in this case, as I've said already, the NH3 is accepting a proton from H2O. Therefore, the H2O is the acid and the NH3 is the Bronsted-Lowry base. Okay. Using Bronsted-Lowry theory, substances not previously defined as acids or bases now fall into these categories. But water falls into both. And I just want to go back there for a moment and go back to this one. What did we say here? Water was accepting a proton. Water was a base. Go forward a couple of slides. Water is now a Bronsted-Lowry acid. So water can be an acid or a base depending on whether water is donating a proton or accepting a proton. Extremely important. So water can act as both. And any substance that acts as both an acid or a base, depending on what it's reacting with, is called, and that's the word you've got to remember, it's called an amphoteric substance. Okay, so water will donate a H plus to ammonia. That makes it an acid. Water will receive a H plus from HCl, making it a base. So because water can be either an acid or a base, depending on what the other substance wants to do, water is therefore an amphoteric substance. It can act as an acid or a base thanks to the strength of the Bronsted-Lowry definition. It's extremely important. So here's an example. HCl and H2O. Take a look at all these. Okay. First of all, we've got the H2O becoming H3O plus. So the H2O has received a proton, meaning that's the acid, that's the base. Okay, so in this case, water is a base. The next line, we notice that the NH3 becomes NH4. So now we notice that NH3 has picked up one. So now the water is donating a proton to the ammonia, making the water this time an acid. Hence the reason why we call it an amphoteric substance, because it depends on what the water is reacting with before we can put water into the category of acid or base under Bronsted-Lowry theory. This one, HCl and NH3. Look at what happens. We've got to go over here. NH3 has become NH4+. So that means that the NH3 has accepted the H+. So it must have travelled this way from the Bronsted-Lowry acid to the base. And finally here, and this is most interesting, sulfuric acid, or hydrogen sulfate, and nitric acid. Look at what happens when both of these meet. The HNO3 goes up to H2NO3+. So this one has accepted a proton. It's gone up by H+, meaning that there has been a transfer of a proton from what we call sulfuric acid to nitric acid, making sulfuric acid a Bronsted-Lowry acid, and nitric acid becomes a Bronsted-Lowry base. Now do you see why Bronsted-Lowry theory is far more superior to Arrhenius? Arrhenius was way too narrow. So when we open it up to the action of a donation of a proton or the acceptance of a proton, then we know that we can expand the number of substances that act acidically or basically thanks to that definition. So that's the end of that. I'm going to leave you with these questions here. And these questions I want you to work on. They're from your workbook, page 28, question 12.1. If you have your workbook and prefer to work out of it, that's fine. Otherwise, I have them produced here for you to work on. I'm going to ask you to do part A to part J, and I'll correct those at the start of the next class.